This is Francis Bitter's magnet laboratory at MIT. We're fortunate enough to be able to use some of the apparatus here for our demonstrations of magnetic forces. You're all familiar with electromagnets. They consist basically of a coil of wire through which a current passes, producing a magnetic field, like the electromagnet in this doorbell buzzer here. Now, the current requirements of this electromagnet are quite small and can easily be supplied through light wire, like this lamp cord here. The electromagnets in the magnet laboratory are basically the same. They consist of coils through which currents pass, producing magnetic fields. For most of the problems studied in this laboratory, strong magnetic fields are needed, so that the currents through these coils have to be very, very large, and the coils have to be cooled by hundreds of gallons of water a minute. The very large currents, 10,000 amperes or so, reach the magnets through these bus bars overhead, like the one Dr. Bitter will show you over there.
Here we have the bus bars that carry the current around the laboratory and can be fed through switches to any one of several magnets, like the one here. If you close this knife switch like this, to carry the current on to the heavy leads here coming to the magnet. Here, the terminal which brings in the current is connected to a smaller coil which goes from this plate to this one, out of this electrode, out of this bus bar, through this switch, and out, so to complete the circuit. This coil would be melted in a small fraction of a second, I think, if it weren't very effectively cooled by water coming up from below and through the coil and out through these pipes that you see here. This magnet is used to measure the magnetic properties of very feebly magnetic substances. By connecting a specimen from the middle of the coil where the magnetic field is created through a fine wire or string, through this tube here, to this very sensitive microbalance that Mr. Lin is adjusting here, we can measure the very small force which even this strong magnetic field produces on relatively non-magnetic materials like copper, aluminum, oil, water, and so on. Here we have a second electromagnet, and back there a third one. And over here we have a couple of researchers connecting up the very last word in magnets as movable and efficient. As John has said, this movie is about magnetic forces, like the forces of attraction between these two permanent magnets and the forces of repulsion. These are the forces which drive all electric motors. We want to demonstrate in this film that magnetic forces are due to electric currents. This you can show perfectly well in your own classrooms and laboratories with very modest equipment. Since we have here, however, these big currents, we want to use them to put on a new kind of demonstration that we've never seen ourselves. We're going to use the magnet laboratory just for having fun this time. In order to get the currents into these big bus bars, we have to turn on the big motor generator out there. We're going to take you out to have a look at it, and you might notice that very considerable forces are required to move the very heavy machines we have out there. Those are magnetic forces. Okay, Beans, you all set to fire it up?
Yes, sir.
This is the machinery that provides the current for the electromagnet. It consists of a motor operated by current from the power lines and a generator which provides the current for the magnet. I think the size of this apparatus gives you some feeling for the forces that are required to turn it over and some feeling for the current that we will be using in these
first thing we're going to want to show is something about the forces between currents. That's something we know about in the magnet lab, isn't it, Henry?
At least we're finding out rapidly. We sometimes try to generate very high magnetic fields for very short periods of time by putting very strong current pulses through small coils. We just cut open one here, which holds the world record right now.
Yes, the currents go around this way, don't they?
That's right.
Yeah.
Of course, we've made many before this one which didn't hold up, and here's one that blew up. The conductors were forced outward, making it look like a barrel.
Well, here comes John. Now we want to show you something about the forces which currents and conductors exert on each other. These, in general, can be very complicated. In fact, if we wanted to describe the force on some little piece of conductor here due to the currents flowing in the whole thing, we'd have to take all the currents into account. Before we're through, we're going to have to consider the whole idea of a magnetic field to describe these forces. However, to begin with, let's take the simplest case possible of two parallel wires like this and examine the forces which they exert on each other.
The biggest problem I have with that is trying to remember which way the forces go. So we're going to demonstrate it in a way that I think makes remembering it easy. Here we have a bundle of parallel wires, all connected to a bus bar up at the top. Currents flow down through these wires, all in the same direction, and out through this copper strap to another bus bar over there. Okay, let's see what happens when we pass current through it.
All right, Beans, let's have a little juice here, and let's start gently. Let's have about 1,000 amps to begin with. Takes a minute to build this all up.
You're watching on the telephone.
Oh, tell them to call me back later. I'm busy. How's it coming, Beans? You got it? All right, let's go on up to 2,000. There we begin to go.
2,000.
On up to 3. Let's show it really.
3.
Oh, there we go.
4. 5.
I guess that's enough. Let's cut it off. Well, I guess there isn't any argument about which way those forces are working. When currents are moving in the same direction, they attract each other, and you can see that by the squeezing up of this bundle of wire.
You've seen what happens when we have currents flowing in the same direction. This time we're going to see what happens when the currents flow in opposite directions. The current comes in from the bus bar through this flexible copper strap, down through this solid copper rod, and back up the other side, and out this flexible copper strap. Now these are solid copper rods. They don't move easily, and the current on one side goes that way, and on the other side goes this way. Now let's see what happens. You may fire when ready, Maestro.
Okay, Beans, this time I want you to set the equipment so that when you close the circuit breaker, you get the full output of the machine through these all at one crack, and stand by to open it up in case we get any trouble. Okay, let's take it away. Yeah, there it is, going out.
There, you see how far it's spreading apart? Now those are solid copper rods.
There she goes. Whoa, cut it off.
Okay, fire's off.
Did you see the flash out there? That was the circuit breaker that opened the circuit when we were getting too much current through the machine.
Okay, go ahead. 500, 1,000, 2,000, 4, 5.
Let's get going on the next experiment. You make the connections while I say
Okay, I'll go get started.
This is a magnetic compass needle that's used to explore the field of the Earth. And we want now to use a compass needle like this, or a whole lot of them, to explore the field around a current.
Well, here we have a loop through which current comes in to these copper straps here, flows through this loop made of copper bars, out around this way and out through these copper straps.